Thank you, Maria, very much for the introduction and for having me here. I'm Stefana, as she mentioned, but I'm here to talk about robotic fabrication and its role in architectural design. I'll go a little bit into my background just to give you an idea. I started studying in Bucharest, architecture. I then moved to Stuttgart for my diploma, where I worked at the ICD and ITKE. I worked at Knippers Helbig Engineering at Design to Production in Stuttgart, and then went back into academia as a research assistant at the ITKE at the University of Stuttgart. And then in 2014, I moved to Zurich to do my PhD with grammatical research at ETH. And earlier this year, I moved to Princeton, where I started up my labs, the Lab for Computation and Robotics Enabling Architectural Technologies. And together with my colleague Forrest Meggers, who's running the Chaos Lab, we are running the technology department in the School of Architecture, combining our two labs under the very inspired name of Create Chaos. Besides finding funny names and climbing on structures, we try to also do serious things, such as running the PhD in technology track at the School of Architecture. But back to my lab, what are we doing there actually? I like to look at the digital fabrication process, and in particular robotic ones, and the way that computational design tools can allow to integrate these fabrication processes into the design process directly. So if we look at the architectural design as it is, it can be described as the result of many parameters that come together, such as structural parameters, functional ones, geometry, material, or fabrication. And their interactions can be quite complex if we think of the different types of the parameters that are involved in there. This is where I believe computational tools can be really useful for architectural design to control all of these complex interactions. And if we look at computational design per se, as Maria gave you quite a good introduction already into it, I'm trying not to repeat myself, but computational design was initially used in architecture for automating drawing, but not only. So starting with Sutherland's Sketchpad in 1963, this was not just an automation tool of the manual drawing procedure, but it already included topological and parametric relations between the individual elements of the system. Moving on, this quickly developed into design systems where the computational power was used to generate and to visualize a very high number of design solutions, as for example floor plans of different types, and then check them for feasibility. And then the step from checking if many designs fulfill the given constraints to trying to generate designs that directly fulfill these constraints was a pretty small one. And this is what current research in our field is focused on, using procedural or generative algorithms to allow to compute the complex relationships between these multiple design constraints. However, I was talking mainly about fabrication, and particularly because I believe fabrication has kind of fallen between the cracks in this process. So a lot of other parameters, there's a lot of research on how to integrate them, but typically the architectural design process is a very sequential one, with a very clear break between design and fabrication. And fabrication is still mainly a manual process where complex logistics and different fabrication steps are solved usually in a post-design step. Digital fabrication has entered the field only recently, as opposed to other industries where robots have been used for decades to automate the fabrication processes. However, architecture requires the design and the fabrication of individual objects every single time, which does not lend itself for the classical automation procedure. So this is why what we do is we look into robotic processes as ways of overcoming the limitations of manual ones, for example, through the robot's capacity of precisely moving, placing, and holding elements in space. And this can lead to differentiated structures, such as this one from grammatical research. However, the embedding of the fabrication process and their constraints into the design loop is not quite there yet, I believe. Typically, the design space can be described as an intersection of the solution spaces of many given parameters. These are just like selected ones, an example of them. But what often happens with digital fabrication processes is that the solution space is pretty dramatically reduced to what can be intuitively controlled by the designer. And this leads to a very small part of the design space being actually explored after investing a lot of time and energy in developing these very complex processes. So my hope and intention is to expand this given solution space by employing computational methods that have the power to make full use of the possible design solutions. If we look at the construction process itself, and this is the build-up of the Heiler roof of the Block Research Group at ETH Zurich last year, what is striking to me is how much the space changes during construction. So from different layers of materials to the build-up and the taking down of the scaffolding and simply the logistics, fabrication cannot be regarded as a static parameter. And this, I believe, is a major difference to many other factors. So typically, architecture has been designed for its final use, but fabrication introduces a temporal factor that can strongly impact the design. And if we take this temporality of the fabrication process and we apply it to other factors, we realize that actually most of them have a time-related a relation to time in them. For example, structural stability that needs to be fulfilled throughout the entire construction process. But this is very rarely considered during the design process. It's mostly solved by using scaffolds or adding structures material that might not be needed. So the projects that I want to talk about and show you, they look at specifically at this temporal aspect of design and expose the evolution towards a fabrication-informed design process. I want to start with a very old project. This is actually my diploma project from the University of Stuttgart, which I did together with Marco Bauer at the ICD and the ITK in Stuttgart. And back then, this was in 2012, so nearly 8 years ago. No, 7. we were questioning the typical top-down design process by looking into multiple scales of a grid shell structure. And while the project did not really specifically address fabrication parameters, it looked at ways of how to integrate multiple parameters at the same hierarchical level, and it introduced a temporal aspect to the design process. And we did so by choosing an agent-based system that can adjust to external inferences through their position and orientation and through the implementation of simple behaviors. And while the time-related changes do not reflect the actual fabrication process, the pure visualization of the design's generation and just not trying to find the ultimate solution and then showcasing that, but going through it and really following what's happening in there, this allowed us to understand the interactions between the different parameters a lot better, and gives the design process another dimension. So ultimately what we did is we chose different adjustment rules which were informed by lighting situation or the geometry or the structural ones, and then led to completely different shapes purely through the interaction of the agents. Well, this was a purely digital project, which was like a first test of first contact also with computational design methods. The first project in digital fabrication came right after, while I was working at Design to Production in Stuttgart on the solar station. And the constructive system that we developed there was based on a press-fit system of laser-cut bent aluminum sheets. But what became clear was that besides the material behavior and geometric constraints, such as that all the surfaces needed to be developable, that they had to intersect in certain points, the assembly sequence played a major role in the successful buildup of the structure. So the details and the entire geometry were developed such that every part could be reached during the assembly in a given sequence, and such that they fit together like a puzzle and force the material into the required shape. So I looked at projects focused on design and focused on fabrication so far. And the next one was a project that I was involved with at the ICD and ITKE in 2013-14. So that was when I was a research assistant there, which really focused on combining these two processes. So the project is based on biomimetic principles that are abstracted from the beetle's elytra morphology, mainly due to its lightweight character and fiber arrangements. I'm sure a lot of you have seen some of the ICD-ITK pavilions, and they're always based on biomimetic principles and identifying these rules that can be applied to architecture, and this is what we started with in here. So we looked at the beetle's elytra at two different scales to identify, on the one hand side, the overall arrangement of the trabeculae. These are little individual holes in that double layer structure. And then on the other hand, the fiber layout inside each of these little holes and how the fibers are laid out to reach, oops, no. We're gonna have to go through it again. No, I hope not. I'll try to move forward if I manage somewhere. There we go. Maybe we made it till here. Great. Yeah, so we were scanning the beetles and looking into it, into how the fibers are arranged to achieve a structure so light and strong. The design tried to negotiate all of these parameters, so all the parameters involved, including fabrication constraints and geometric rules, into one overall functioning system. They're all encompassed in the one component's definition. So basically in the winding syntax of the base geometry, which represented one of these components. And that was the main computational part to deal with. In addition, we did the structural testing on it to identify areas where it needed structural reinforcement, where then carbon fibers were added to the mix. So these were winded where we identified that the forces would become larger. And in terms of fabrication, we used two robots. Okay, I'm gonna give up on the videos. No, I shouldn't touch my computer while I'm doing this. So now I'm gonna try to move on to the fabrication. That's pretty good. All right. So we used two robots that were synchronized. They were running on a master-slave system, which allowed us a very simple control of the movements. Why we used that is that we didn't need any sort of additional support or mold on which to wind. So the two robots would have frames, adjustable frames on each of their end effectors, and then by moving synchronously, the fibers could be winded upon them without needing a very strong structure in between. You can imagine the tension that's resulting from the fibers being winded and winded is adding up and induces quite high forces into there. So then we had a fixed fiber source, and the robots would be winding around it. And they would wind a carbon fiber, a glass fiber layer first, and then a carbon fiber layer for reinforcement. And now I can actually continue. So the main focus of the project was actually at looking at how information can be embedded into one individual component by generating its geometry such that it can fulfill the multiple constraints. This included structural information, fabrication limitations, and design constraints. And the individual geometry of each of these components is actually a pure result of the fabrication sequence, which is where the time component comes in. So the component is winded by iteratively laying fibers, running in circles basically around it, on top of the steel frame. And as a result, the time-based winding syntax plays a really crucial role, since each fiber tensions the previously laid ones. And the hyperbolic shape is a direct result of the definition of these points, in which sequence they come together. Several layers make up an individual component, ranging from a form-giving one, a glass fiber layer, to two reinforcement carbon fiber layers. And this led to the fabrication of individual components of all shapes and sizes, the biggest one having a dimension of 2.5 meters in diameter. This is not actually the biggest one. There were bigger ones. And assembled into a pavilion, which was extremely light and weighed less than 600 kilograms at the time. So I'll move on to my next project. This is the Brick Labyrinth, which I did during my time at Grammaticola Research. It is also a student project. It's building up on a long tradition of robotic bricklaying. Grammaticola has been doing bricklaying for over 10 years now. So our students were not particularly excited when we told them we're doing bricks again, putting them together. But what really differentiated this project from any of Grammaticola's previous ones is that we didn't use any type of mortar or glue. So they are purely dry stacked. We wanted to have a reversible process so that then at the end of the day we can take the bricks apart and send them back where they came from. The main challenge for the students this was to develop a design that was stable, that was buildable with 2 robotic arms that we had at the time, and in a very short time frame. This is an 11 weeks project that we did. So through the precision of the robots, the students got to explore both the structural limits of compact brick assemblies, as well as different possibilities that the bricks could be assembled together by varying the distances between them. And they developed a new brick bond system, the Image C, which made use of a transversal bricks position, and through the shifting of these transversal bricks, we could actually control the center of mass of the wall. So this could be adjusted to help achieve stronger leaning walls. This resulted in a spiraling labyrinth that was leading a visitor through the different qualities of the brick bonds. So I'm not going to touch the video, but the robotic fabrication process directly influenced the design, of course. This was built in our robotic fabrication laboratory at ETH Zurich, where we have 4 robotic arms that are hanging on a gantry system, so we could reach a very, very large space. The CAD model is translated into robot movements and then sent to the machines through a custom interface, allowing real-time adjustments to the design through the building process. And we used 2 of the 4 arms to work together, which were parallelly positioning the bricks to increase the speed of the process. So in this case, the 2 robots are not cooperating. They're purely used to speed up the process and to allow us to build a large structure. It consisted of over 10,000 bricks in a very, very short time. In addition, the robots had to be synchronized time-wise so that one doesn't get a lot faster than the other one, and we had to make sure that the sequence actually avoids any types of collisions. So dividing the geometry of the labyrinth in a sequence that ensures that there's no collisions between the robots and that all bricks can be reached, that they can be approached from a direction where there's no other bricks in the way. That was one main part of the process. We developed a custom End Effector, a brick magazine that could pick up 8 bricks at a time. This was the maximum payload that we could get out of those robots. They have a 40-kilogram payload. I think we went a bit overboard. But this again allowed us to speed up the process quite a bit. Also because we had to run them in manual mode, so we had to move the robots very, very slowly, purely because of the type of structure that we were building and because we were working with students. So the robots were moving at some 250 millimeters per second, so we tried to do everything we could to speed up everything around it. We had a type of labor division between our robots, so we used the little UR5 arms to prepare these brick stacks, basically to automate the whole process and also to keep a bit of a distance from the labyrinth. So we tried to keep students out of it during construction, and this really helped not having to be too close to the robots and the structure. And we had 2 of these pickup stations on each side of the lab, again to speed up the process so that depending where the bricks were placed, the drive back and the drive to the labyrinth would be as short as possible. One task that was coming together with the sequence was not only how to reach every brick so that the robots don't hit each other, but also so that the robot end effector doesn't reach the neighboring bricks. So we also had to consider the approach direction and which robot could place which brick to make sure that they're all getting there. And then this was built during a time frame of less than 4 weeks. I think 3.5 weeks. We managed to build the whole thing. We also did the build-back process. Well, we tested the build-back process, which literally worked by reversing the code. We didn't do anything else, which was pretty amazing. But then we decided to take it down by hand because it was a lot faster at the end of the day. All right. So one main challenge, as you might imagine, was the stability. Bricks stacked without any mortar, 3-meter-tall walls, and 17 students. That's quite a recipe for disaster if we don't think about it too much. So what we did is, together with the students, we developed a geometric stability analysis. A very simple process. So we managed to calculate whether a wall would be stable just in terms of geometry without using any types of fancy FE solvers or programs that neither us or the students could use. Of course, this is not reflecting reality one-to-one, but it was also a great exercise for the students into computation and figuring out how to go through the system. And what's important here is that the stability check, again, had to really go through every single layer of the brick wall. So we couldn't just test for the last step. We had to test every single layer of bricks that were in there. So what this allowed us to do is we could easily identify situations where the structure fails geometrically by running the simulation at every layer, and it would tell us quite reliably where it would fail. We tested it with empirical tests on single wall structures, and surprisingly, they did fall where we expected them to fall. But what we also did is, through experiments, the students discovered that double-layered walls provide additional stability through the friction between the bricks that are connecting two walls. So they added this transversal wall to it, which then keeps the two leaning walls together. And this friction is, of course, not included in the geometric analysis. So the limits of this system were tested physically, and then employed in the bigger prototype to achieve leaning walls through, cantilevering bricks, which were a crucial part of the Brick Labyrinth experience. And this is where they came in together. So these transversal walls hold the structure together, ultimately resulting in the successful fabrication of the whole labyrinth. And I'll let my colleagues David and Luca, we were teaching this together, take you through the labyrinth. I wasn't there the same day. I'm really sad that I don't have a video of it, but yes, this maybe helps experiencing the entire feel of the labyrinth. And as a summary of the whole project, I think what's really striking, or what I took out of this project, is that the sequencing and the time parameters, they clearly don't just cater to the fabrication procedure. It's not just about how you reach every brick and how you build this whole thing up, but also to the structural one. So that started to get me thinking on, is this sequence, assembly sequence and time, is this something we should actually look into at every step? And this leads me to my last project, which is actually my PhD thesis. I was looking at design and assembly processes with multiple robot arms to create differentiated spatial metal structures, which can make use of the geometric complexity that can be achieved with robots in order to use material more efficiently. So going back to the robot's basic functionality of being able to move, position, and hold elements in three-dimensional space, it lends itself really perfectly for bespoke assembly tasks. So using two robots as opposed to one, in addition, that adds to that task through being able to give the robot another role in the process. So the robots here serve not only as agents that were positioning elements, but at the same time supporting the structure. So the assembly process works as follows. You have one robot that brings one element, and you have the second one bringing the second element. And once the connection is done, in this case we did it by hand manually, one of the robots can let go again and bring a new element, but the other robot stays connected to the structure. And this process is repeated over and over again until a stable configuration is found. So what happens is that one robot is always attached to the structure, and it can serve as support for the structure during the build-up and also as a geometric guide, so you avoid deformations and large tolerances. The geometric system that the structures are based on is using an aggregation of tetrahedral elements. So volumetric non-directional geometries that can expand in all directions, and they can vary their density through the differentiation of the element's length and the attachment angles. These tetrahedral elements consist of 3 bars. I call them 3-bar groups. Oh, sorry. My hair into the microphone? Sorry. Which are sequentially added, and they are allowed to interact. The only goal is to provide a statically determinate geometry. So at every step after placing 3 bars, the structure is again stable. And as I mentioned, everything's based on the sequence. In this case, 1 point and 3 bars are generated at every step of the design process. One crucial element is the node. Space frames live through their node, and their efficiency and functionality is defined very much by it. Classical nodes connect in 1 point, but they require a prefabricated connection element, which, if you want bespoke angles, it would require individual connection elements. And this is why I was searching for a node that can be fully integrated in the robotic process, and through shifting bars along their neighbors, this would lead to a connection where only 2 bars connect in 1 point. So for this reason, I expanded the existing space frame nodes first by shifting their joints, so shifting the elements along their neighbors, which simplifies the connection, but at the same time it introduces bending moments and it reduces the stiffness of the entire structure quite dramatically. So in a second step, I added a second connection point for every bar at the connection, which then stabilizes these connections. So it introduces a lot of stiffness and actually reduces the deformations in comparison to the classical node where they all come together in 1 point. What this means, though, geometrically, is that every rod connects to the existing ones in at least 2 points at each end, depending on the sequence that it is added to. And in order for this to work, I had to look at the geometric dependencies in one of these connections and find the position of each bar such that these perpendicular relations are fulfilled everywhere in the structure. This, again, is extremely dependent on the sequence. So if we look at the bars as they are generated one by one, the first one can be calculated quite directly because you have a point and 2 bars that the resulting bar should be tangent to, and this is a deterministic problem, can be directly calculated. However, the second and the third bars in a 3-bar group, they have more unknowns, as you don't have the point anymore known at the top of it, so you need to figure out where is it touching the first bar as well. So this required an iterative process to calculate each of these bars' positions. But this allowed to fabricate quite intricate nodes, as for example this one consisting of 16 bars that meet at 1 point, where each bar connects to the structure in at least 2 points. So adding new and new bars, there's more and more connection points coming to it, but even though they look pretty random, they really are not. With regards to fabrication, I used 2 robot arms, 2 different setups, a smaller scale one or medium scale one with stationary robots, and then the robotic fabrication lab again with 2 of the large robots working together. I tested different materials and connections, from aluminum with wires to glued connections that required a custom milled notch, and then ultimately ended up with steel and welding, basically because it simplified the process and it provided the necessary stability and stiffness into the structures through it. The welding process is implemented manually, while the robots are used purely for positioning and holding of the bars. And this is me at my very first welding tests, tryouts. I got a lot better at this during the time. And then it finally resulted in quite beautiful, complex nodes, I would say, and structures that could go up to 4.5 meters without a problem. However, working with two robots in a common workspace with a constantly changing structure implies a very high probability for collisions, which is why my colleagues, Gonzalo Casas and Augusto Gandia, they developed an interface to a robotic simulation environment that utilizes existing path planning algorithms for the calculation of collision-free paths. So what this allowed me to do, this whole path planning process, is to generate these intricate paths to insert the elements in the existing structure without collisions, while ensuring the geometric integrity of the double tangent connection that I developed. So bars would literally have to be inserted in a specific movement to be able to connect to their neighboring bars in the required points. And I have a lot of these videos because I think they're really, really pretty, but I'm going to start skipping them slowly. This enabled a first large-scale prototype to be built, and while the robot setup allows the robots to reach almost any point in the workspace of the lab, the whole path planning process unraveled what impact the sequence has on the feasibility of these structures. So paths could not be very easily found. It was quite a struggle to set the parameters and find the starting position and the final one such that a path could actually be found. But what we found out throughout the process is that one main parameter that really helped in this process is the sequence. Again, I need to stop doing this. Sorry. By regenerating the bars in a different sequence, we would very often be able to find the robotic path, the collision-free path. So this was the main parameter to go when nothing else worked. And besides the fabrication process, I also looked into the structural integrity, for which reason, together with my other colleague, Thomas Kohlhammer, we developed an interface to an FE solver to be able to automatically translate the geometric model into a structural one and read out stress and deformation utilizations, which could then be used within an optimization process for the design. After all of this information, so developing all these individual parts of fabrication and structure and geometry and all of that, the question still remained how to use them in a coherent design process. And due to the strong role of the fabrication process, I chose the sequence to be the base of the design, meaning that the geometry is really generated in the exact same order as it is fabricated. Which defined not only the geometric relations between the bars, but also how the structure performs structurally and whether it's feasible in terms of fabrication. And in order to combine the very different types of design variables from discrete to continuous ones into one common process, I chose to divide the design process into individual steps that each target one goal of the design and one problem of it, so to say. So in the first step, what happens is I have a boundary volume, and nodes are distributed throughout this volume at a minimum distance between each other. In a second step, the topology is defined. So I decide which point is connected to which other 3 points. And this topology remains unchanged until the design process is finalized. And then in the next step, the topology stays unchanged, but then the third step searches for the ideal position of the nodes in terms of structural performance through an optimization process that happens there. And ultimately, in the very last step, robotic paths are generated for the fabrication. This division of the design process allowed to apply individual algorithms for very targeted problems, which then led to a simplification of the design problem as a whole. However, it does come with its own downside because it introduces a hierarchical dependency between the individual design steps, which means that every step's output needs to ensure that the next step can have a design solution in the first place. So this is one crucial link between the individual steps, which needs to be considered when dividing the problem this way. And I'd like to finish this project with a few images of the largest demonstrator that I built that consisted of 210 bars and 279 connections, and this was built at the end of my PhD using the 2 cooperating arbs in the RFL over a period of 3 weeks. And there it is. And ultimately, this was tested very, very scientifically by people that are in this room as well, but we had a lot of fun with it. It's holding, it's working. So this is where I was. I showed you a lot of the projects that I did during the past 10 years. This is where I am right now. This is our lab in Princeton. It never looks as clean as in this photo, but it's a really great lab. We have robots of all sizes and colors and payloads and reaches. We're pretty spoiled, and we've used them for student projects to explore the versatility of the robots through setting up very different processes. And what this actually made me understand, or what I focused on during all these projects, was that in our field, you never just design the object, you design the entire process, the entire robotic process. And this includes the robotic setup and the tooling as well. So the result is so strongly affected by the setup that you use. If you have a relatively small setup, you can build small structures, whereas with a different one, you get a completely different solution space. So this made me question how we design the structures to fit a certain setup and material after we define the construction process. This is what we usually do, and why we don't regard the design of the setup and the tooling and the material as equal parts of the design process, particularly if we have these tools available. And robots are versatile. They're easy to plug and play, switch around, get a bigger one, get a smaller one. Usually that's not a big challenge. So ultimately, that would lead us to design the object that we want to build, but also its structural behavior and its material, as well as the fabrication setup and the tooling that we need in the same common step, while keeping in mind the temporal aspect of digitally fabricated structures and how the design of all these things can be adjusted throughout the construction process. And with this, I will finish. Thank you very much.